Okay, any questions? Now there is one. Okay, so here is the question. So we said that the force, the magnetic force acting on charges is proportional to the speed of the velocity of the charge. And we also started with the observation that if I have this magnet, which creates a magnetic field, and if I put it over here, it just sticks. So there are no charges in motion there. So that's basically the question. Now the answer to this question, also the answer to why do we have permanent magnets, is actually the same. Now we have these electrons in making everything. Now the electrons, you can imagine them, okay, this is a wrong description, by the way. Don't repeat this description in your modern physics or quantum mechanics courses. But a wrong description of an electron is as if you have a very small sphere. This is our electron. And it is rotating. So it has some angular momentum in that direction. So in this picture, which answers your questions, you see the electron is a charged object. So as it's rotating, its charges are moving. So the electron creates a magnetic field because there are moving charges in the electron. And it also feels the magnetic force because there are moving charges in the electron. Of course, this is, I repeat, this is a bad picture of the electron. It just isn't correct in most aspects, but nevertheless, this picture can be used to understand why the electron creates a magnetic field and the electron feels this magnetic force, even if it is not moving. Now, the magnetic force due to this motion or due to this property is not included in this picture, unfortunately. I mean, if you want to take those effects, the rotation of the electron as a whole around itself, its spin, then we have to modify this picture a bit. Other questions? And what will be the direction of this force? I mean, okay, so unfortunately I forgot to bring a second magnet. We know that this is magnetic. This is not magnetic. It doesn't stick over there. The blackboard is not magnetic, so it doesn't stick over here. So only thing is this one. This is magnetic, and it just sticks to both the blackboard and also to this fridge magnet. But if we had two magnets, one thing we could have checked is that this is my magnet. It has a north and a south pole. If I bring a second magnet such that the north pole and the south poles of the two magnets are close to each other, in this case they will attract. They will be exerting forces on each other so that they will try to move together, closer. Now, if on the other hand, we just bring the south poles together or the north poles together, then the force will be just in the opposite direction. So they will repel each other. By the way, this is also analogous to what happens in an electric dipole. You see, if you have an electric dipole, which is nothing but a positive charge and a negative charge, this is one dipole. Let's say this is the second dipole. If you bring the positive end of one dipole close to the negative end of another dipole, they will pull each other together. But if we bring the negative ends of both dipoles together, closer, they will repel each other. So in this sense also, the magnetic dipoles and electric dipoles are quite similar. Both of them do not carry net charge, whether the electric charge or magnetic charge. The electric or magnetic field lines, they look quite similar. The forces that they exert on each other will be, in fact, identical. There will be only a modification of the relevant coefficient of the force that we will see, but the behavior will be identical. Any other questions? Now let's see some other alternative uses of this magnetic force. So we had already seen one case where if you have a region of uniform magnetic field, if you send a particle with a given velocity, it will be mainly do uniform circular motion. So do you know auroras or the northern lights? Yes or no? Yes. So basically, if you have probably seen some pictures of the northern hemisphere or the southern hemisphere. Well, since the northern hemisphere is populated, it will be more common over there, where you have all these lights in the atmosphere. And it's said that they are due to the solar winds. Now, what's actually happening over there is the Earth has a magnetic field. What is the magnitude of the magnetic field of Earth? Average. Any idea? Well, suppose you were kind of trying to study the magnetic field of the Earth. You are the first one to study. And you have to choose some unit, right? So what would you use as the unit of measurement? Okay, Tesla, what is Tesla? I mean, Tesla came afterwards. You would rather, I mean, if you are studying the magnetic field in general, and the main magnetic field that you know is the magnetic field of the Earth, you would just choose a unit such that the magnetic field of Earth is just one Gauss. This is the unit of the magnetic field. This is approximately average magnetic field of Earth. Now, of course, then we started building some standards, and if you just look at the definition of the magnetic field, this is basically our definition of the magnetic field. The unit is kind of fixed. The unit of the magnetic field has to be equal to, what's the unit of force? Newtons. What is the unit of charge? Coulomb. Of velocity? Meters per second. Or newtons per coulombs per second times meters, newtons per ampere meter. And this is Tesla. And 1 Tesla is actually a huge number, a huge magnetic field, and it corresponds to 10 to the power 4 Gauss. These are the units that we will be using. Now, for Earth, if you are studying the magnetic field of the Earth, the natural unit would be just to give it 1 unit to the average magnetic field of Earth. Now, let's say that we have a region of space where the magnetic field is again uniform. This is B. Now, before we studied the example where the velocity vector was perpendicular to the magnetic field. So, in the previous example, this was the direction of the velocity vector, let's say. This is our previous example. And we know that if this is the direction of the velocity vector, then the trajectory will be just circles. It will be circling around the magnetic field line. What happens if the velocity vector is in this direction? What will be the direction of the force? Well, it will be again horizontal. You see, the force acting on this charge will be horizontal. The force acting on this one will also be horizontal toward the center. So the horizontal motion of the object will again be a circular motion, but there is no force in the vertical direction. There won't be any component of the force in the vertical direction, basically because the magnetic force is, well, we already said that it is perpendicular to the velocity vector, but it is also perpendicular to the magnetic field vector. So there cannot be any component of the force in the direction parallel to the magnetic field. So the component of the force parallel to the magnetic field will be 0, which just tells me that the acceleration in the vertical direction will be 0. So the vertical component of the velocity of my object will be just constant. It will just keep moving upward, as if there was no magnetic field. But it will be also in the horizontal components, they will just circle, just like this example. So if you just combine the motion, you are circling around an axis, but at the same time you are moving in the direction of the axis, so you will just be spiraling up. So this will be the motion of my object. It will just make a spiral. Now let's imagine Earth. This is Earth. It has a rotation axis. On the average, it will have some magnetic field lines that will look like this. These are the magnetic field lines of Earth. Where is the North Pole? No. The magnetic North Pole is on the south. Because the north of a magnet is attracted to the south pole. Okay, so let's see. We have the sun. Sun is somewhere over there. It is constantly emitting particles. It is sending towards us many electrons and protons. So let's just imagine an electron that reaches here, or a proton, a charged object. Now there is a magnetic field of Earth. So it entered a region where the magnetic field became stronger and stronger. But if there is a magnetic field, then the motion of the object is just spiraling around the magnetic field. So it will not keep moving. It will just spiral around the magnetic field. So this, let's say this charged object from the sun, when it approaches Earth, it will start spiraling a magnetic field, and well, it won't be perpendicular if it is not perpendicular to the magnetic field line, and it won't be as long as it's not coming through the equator. So it will be moving either towards the North Pole or towards the South Pole. So all the charged objects will be moving towards one of the poles. Now, the magnetic field is not uniform. So we will not be studying the motion of charged objects in non-uniform magnetic fields. But basically what happens is, if the magnetic field lines come closer together, this charged object will feel a backward force. So the trajectory of this object will be, okay, it arrived close to Earth, then it started spiraling around the magnetic field line, it moved to the North Pole. As it's approaching the North Pole, it will feel a force in the opposite direction. And then it will move towards the other pole and back again. So it will just move between two poles. So all the charged objects coming from the sun, they are kind of trapped in these magnetic field lines. I mean, you will study that in your third year. So what kind of a force, what kind of a motion the object will do if it is moving in a region where, I mean, you see, we said that the force will not have a component in the direction of the magnetic field line, but if the magnetic field lines are bending, then things get more complicated. Because, okay, the direction of the magnetic field line changes, the direction of the velocity is constantly changing. So the net effect turns out to be that as it's reaching a region where the magnetic field lines come closer, there will be a backward force. So these are called Van Halen belts. And we will study in the future lectures towards the end of the semester. Here, well, the circular motion is accelerated motion. But here there is an additional acceleration due to this force backwards. So these accelerated charges, they emit light. So this is why you observe lights in the North Pole and also in the South Pole. All these charged objects, they are moved to the poles, either the North or the South, where they are accelerating and they will be emitting charge. They will be also concentrated over those regions. They will be hitting the atoms in the atmosphere, causing them to emit light also. So that's how the lights are formed. Now let's do another example. Let's say that we have a parallel plate capacitor. Now, any questions on this one before we pass on? Well, basically on this one, why the object is spiraling around magnetic field lines. It's not making a circles if it has a component in the direction parallel to the magnetic field line, but rather it will be just going along a helix on the magnetic field line. Any questions? Okay, do you agree that the force acting on my object will be always horizontal, perpendicular to the magnetic field line? But that means that the vertical component of the velocity, I mean, if you remember the mechanics courses, we said that we can divide the motion in 3 different components. The x component, the y component, and the z component. We can just treat them separately. Well, of course, in this case, the force will depend on various components, but nevertheless, if you say this is the z-axis, there is no force on the z-axis in the z direction. So the motion of the object in the z direction is motion with constant velocity. Whereas in the xy plane, it will be doing a circular motion. So if you just combine these two motions, the circular motion in the xy plane plus uniform translational motion in the z plane, you obtain a helix. As it's doing the circular motion, it's also moving up. So this will be the trajectory. Now let's take a capacitor, parallel plate capacitor, which we can use to create an almost uniform electric field. Let's assume that this is the direction of the electric field. And let's suppose that I have some positive charge Q moving in this direction with a velocity V. What will be the direction of the electric force acting on this? Well, if it's a positive charge, it will be in the same direction as the electric field. Agree? This is the electric force. Now let's also assume that there's a magnetic field in this region, in exactly the same region. And the magnetic field is uniform into the screen. What will be the direction of the magnetic force? Up or into the screen? Well, this is V, this is B, V cross P is pointing upward. So this is the direction of the magnetic force. Well, we also know that, let's say this is the z-axis, so the electric force is nothing but Q times E in the minus z direction, and the magnetic force will be Q times V times B in the z direction. The total force acting on the object is just the sum of these two, which is Q times minus E plus VB in the Z direction. Well, one thing is this will be equal to 0 if V is equal to E over B. So now we have a velocity filter. You can, by connecting this capacitor to a given voltage supply, you can determine what E is. By choosing your magnet, you can fix a suitable value of B. So you know what E and B are. And only objects that have this speed, they will be just moving straight. Now, you see, if you have many particles, suppose you create this system, you create a capacitor with a given value of E and a given value of B. And then you send many particles through it. If you send many particles through it, there will be some of them that will go straight through. Those particles will have this velocity, this speed. Now, if let's say, rather than this one, if you have, let's say, you send a beam of particles with a given velocity, and you just, by changing E or B, you can just change in which direction they go. Yeah, that is basically how all television sets used to work. So we have this electric field and the magnetic field, which controls where each electron is moving on the screen. And when the electron hits the screen, it would make a light. So you would be creating this image. Or, yeah, okay, that's it. Any questions? Let's look at another phenomenon. A phenomenon called the Hall effect. This is a device that we can also use. We also use to determine the drift velocity of objects. Now, the idea is this one. You take your conductor. This is your conductor. And you send a current through it. You connect it to a battery, so there will be a current running through it. So let's say if this is a metal, there will be electrons moving around. So your electrons will be moving in this direction. This is the positive, this is the negative terminal, on the average, with the drift velocity. And let's assume that we put this system in a magnetic field. And the direction of the magnetic field is into the screen. So what will be the magnetic force acting on these electrons? How many of you say it will be downward? How many of you say it will be upward? Well, the majority loses. The force is upward. V cross B is downward. But remember, the force acting on the electron is minus E times V cross B. V cross B is downward, but the charge of an electron is negative, so it will be moving upward. So the electron, as it's moving through my conductor, it will feel an upward force. So the electron, rather than moving straight, it will just move up. This will be the trajectory of my electron. So there will be electrons accumulating at the top edge. So the top edge becomes negatively charged because of the magnetic field. Well, if the top edge becomes negatively charged, the bottom edge will be positively charged. As the current is running, let's just assume that initially we have our conductor. There is no current. Then we turn on the battery, so the current starts running through my system. Well, as the current is running, there will be more and more electric charges accumulating at the top edge and also at the bottom edge. But these additional charges will create an electric field. And the direction of the electric field will be down or up? The direction of the electric field will be upward. As more and more charge accumulates, the magnitude of the electric field will keep on increasing. And it will keep on increasing until the electric force acting on my charges will be equal to the magnetic force acting on charges. So in this case, until the electric field just becomes V times B. Now, of course, the electric field inside the metal, we cannot measure it directly, but we can measure, let's say this is A, this is B. We can measure the potential difference between point A and B. What is the potential difference between A and B? It's the electric field times this distance. We know the electric field. Vd times P times L. Of course, it will be increasing initially, but eventually it will satisfy this condition. And once this condition is satisfied, the electrons will not feel any net force, so they will just start going straight. So the drift velocity will be nothing but VAB divided by B times L. So this is a means of directly measuring the drift velocity. Now we could also derive the drift velocity from the given current. If we know the current and the geometry of our conductor, we could just relate them to the drift velocity. We could obtain the drift velocity, but now in this whole setup, we can just measure the potential difference between these 2 points A and B. And that would give me what the drift velocity is. Now, there's another nice thing about this whole effect. Let's just assume that we have this weird material in which it's not the negative charges that are moving, but positive charges that are moving. So instead of just this conductor, I can imagine, I don't know, some liquid solution which contains ions, let's say. This is my setup. I have identical setup using a different material to conduct the charge. There is a magnetic field into the screen. But this time we will assume that it's the positive charges that are moving. Okay, so what is the direction of the force, the magnetic force acting on these positive charges? Downward or upward? Upward. So this is the direction of V, the magnetic, this is V, this is B, V cross P is upward. So this is the magnetic force. So the positive charges will be moving on the upper edge. And the lower edge will be negatively charged. You can just repeat the same procedure. You will get the same whole potential difference between the point A and B with the opposite sign. Just compare the two. If the charge carriers are negatively charged, the upper edge is negatively charged, the lower edge is positively charged. If the charge carriers are positively charged, then the upper edge is positively charged and the lower edge is negatively charged. So now we have a way of determining what are the charge carriers. You see, the direction of the current is independent of the charge carriers. Even if here we have the negative electrons are our charge carriers, the current is running from left to right. Here it is the positive charge carriers, the current is running from left to right. So just looking at the direction of the current, we cannot really say what are the charge carriers. But now this Hall effect gives us a way to measure the sign of the charge carriers. The only thing we need to do is just create this conductor, thin conductor, set a current running through it, put a magnetic field perpendicular to our conductor, and measure the potential difference. If the upper edge is at a higher potential than the lower edge, then the charge carriers are positive. If the lower edge is, if the upper edge is negative, lower potential than the upper edge, no. If the upper edge is at a lower potential than the lower edge, then the charge carriers are negatively charged. So we can directly probe the charge of charge carriers. Any questions on this one? And furthermore, I mean, this relation, there are various ways of using that relation. Now, we had already seen that the drift velocity depends on the electric field that you apply or the potential difference that you apply. But for a given material, if you apply a given potential difference, then the drift velocity is kind of constant. L just depends on the shape. So here we have a means of measuring the magnetic field. So suppose we don't know the magnetic field. The only thing we have to do is just pick up a system in which we know the drift velocity, we know the geometry, the size of the system, just measure the potential difference, and that potential difference will be directly proportional to the magnetic field. So we can determine the magnetic field using this Hall effect. Okay, let's do one more application and then give a break. Suppose we have a region of a uniform magnetic field. And we have this rod conducting, and we push it with a force F, with a velocity V in that direction. It's a metal, so the electrons are free to move. Now, what will be the direction of the force that the electrons feel? Well, let's see, V is in that direction. B is into the screen, so V cross P is upward. The electrons are negatively charged, so they will be feeling a downward force. So the electrons will be moving downward. They are free to move. But if they are moving downward, it means the lower half will be charged negatively, upper half will be charged positively, which creates an additional magnetic field. Electric field, sorry. So there will be an electric field created. And its direction will be in this direction. This is the newly created electric field. And again, there will be the electric field will increase until it reaches the value E is equal to V times B. And then the electrons will stop moving because the net force acting on a given electron will be 0. Now, any questions on this one? But now let's imagine one thing. Let's assume that this rod is not so short. Well, it's up to here. And we connect it to our resistor. What does a battery do? We said that the battery just takes electrons from one side, gives electrons to the other side. So what does this do? As this rod is moving, it will be pushing the electrons downward. It takes electrons from here, pushes it over here. So as long as the rod is moving, there will be a current running through the circuit. It will behave like a battery. So this is our first simple electricity generator. If you have a region of magnetic field, just move a conductor in that magnetic field, so it will create a current if you connect it to a circuit. No, this won't be an alternating current. I mean, the electrons are always moving in this direction. So the current will be always in the clockwise sense. It will not change its direction. The current always moves in this configuration, the current will always be moving in the clockwise sense. But hold on, there's a problem though. Okay, we said that the kinetic energy of an object in a magnetic field does not change. It basically means that we already know that the work done on an object is equal to the change in its kinetic energy. So if the kinetic energy is not changed, so there is no work done on the object. So magnetic field, the strong magnetic field so the magnetic field doesn't do any work on charged objects because it doesn't change the kinetic energy. Right? No? You don't remember? You see, we always said that the force of the magnetic field is always perpendicular to the velocity. Fb.dl, Fb.v, this is always equal to 0. The magnetic field acting on a charged object multiplied with the velocity is always 0, because the magnetic field is always perpendicular to the velocity. Let's say that we wait for a small amount of time dt. V times dt, this is equal to 0. I just multiplied the upper equation by dt. But this is nothing but the very small displacement of my object. But the force times dl is nothing but the work done by the force. The work done by the magnetic force is always 0. Do you agree? But let's come back to this example. We said that there is the rod is moving in the magnetic field, so that if you connect it to a circuit, it will create a current running through the circuit, but the current will be some of the energy of the current will be dissipated in the resistor. So where does the current come? Where does that energy come from? What is doing the work? So something should be doing some work so that we dissipate that energy in the resistor to conserve energy. It's not the magnetic field that is doing work. So what should be doing work? Electric field? Well, where's the electric field?
In the rod.
What creates the electric field? You see, before connecting it to a battery, there were no charges. Okay, we will be discussing this example in the next hour. Let's give again a 10-minute break, not longer. So I'm waiting for you at 2:30.